Ever wish you could throw a piece of plastic on the ground and have it decompose like an apple? With biodegradable polymers, this, as well as much more, is possible. How do you like them apples? In this presentation, I, Brett, along with Reagan, Lauren, and Lisa, are going to be going over a general overview of biodegradable polymers. We will first begin in defining biodegradable polymer and what polymer degradation means. We will then go into the chemistry behind biodegradable polymers. We will explore the applications of biodegradable polymers and conclude with the advantages and disadvantages. We will first start this presentation with defining the term biodegradable. Biodegradable, at the most basic, simply means an item that has the ability to break down or decompose back into the natural environment without causing harm. The American Society for Testing Materials, ASTM, and the International Standards Organization, ISO, define degradable plastics as those which undergo significant change in chemical structure under specific environmental conditions. Now that we know the exact definition for biodegradable polymers, we will show you this on a more visual scale. Polymer degradation is a change in the properties, tensile strength, color, shape, etc. of a polymer or polymer-based product under the influence of one or more environmental factors, such as heat, light, or chemicals. Originally, polymer degradation was viewed negatively because of the properties and performance deteriorates with time. However, polymer degradation is now known to offer many advantages, leading to different applications that will be discussed later in this presentation.
A general statement regarding the breakdown of polymer materials is that it may occur by microbial action, photodegradation, or chemical degradation. All three methods are classified under biodegradation as the end products are stable and found in nature. Biopolymers designed to be discarded in landfills, compost, or soil are broken down by microorganisms via microbial action. Photodegradable polymers undergo degradation from the action of sunlight. In many cases, polymers are attacked photochemically and broken down to small pieces. An application for biopolymers which experience both microbial and photodegradation is in the use of disposable mulches and crop frost cover. Chemical degradation, which will be discussed next, is used in medical applications.
Enzymes can degrade by different mechanisms such as enzymatic degradation and hydraulic degradation. Enzymatic degradation is when an enzyme is used to break down a substrate, as shown in this image here. As you can see, the substrate comes to the enzyme to form the enzyme-substrate complex. Enzymatic degradation assists with biological polymer breakdowns. This mechanism is also used to break down proteins. In addition to enzymatic degradation, polymers can also be broken down by hydrolysis. As a mini refresher, many of you probably remember that hydrolysis is the reaction where water is added to break down a molecule, like in this top example. Here we have an amide being broken down into carboxylic acid and amine due to the addition of water. Hydrolytic degradation is the breakdown of the polymer by water. The water cleaves the polymer, which leads to the formation of monomers.
Now that we've talked about the chemistry behind biodegradable polymers, let's go into the applications of it.
The need for biodegradable polymers is urgent. Millions of tons of plastic are added to landfills globally each year. Recycling and incineration are alternate routes of disposal. However, they are very costly, particularly for smaller items. Conventional plastics, like polyethylene, can take more than 100 years to degrade, thus taking up large amounts of space in landfill sites. By using biodegradable polymers, landfill sites can be reduced by 20 to 30%.
As previously mentioned, there is a huge need for biodegradable polymers due to landfill issues. However, the uses for these polymers do not stop there. Biodegradable polymers have a large number of applications in the medical field, with more breakthroughs every year. Another large application for biodegradable polymers are plastics. especially the ones that end up in landfills. These polymer applications are even being used in the agricultural industry using many modified technologies already used in the medical and plastics field. There are many uses for biodegradable polymers such as trash bags and food packaging. A commonly used biodegradable plastic is PLA, polyactides, which are starch-based. Another type of plastic is cellophane, which is derived from plant and tree cellulose. Biodegradable plastics are also used in agricultural industries. The easiest example is agricultural film, which is used to increase soil temperatures and reduce weeds.
The medical applications of biodegradable polymers covers a large span. They can be used for implants for vascular or orthopedic areas, such as stents and screws for bone healing. They are used for suturing, which is basically the thread used for stitches. The glue that is used to close incisions is also a biodegradable polymer. Biodegradable polymers have a large hold in drug delivery as well. This includes capsules used to encase drugs. They are also used for drug delivery, but for long-term drug release. The idea is, as the polymer slowly breaks down, the drug slowly gets released. Lastly, for drug delivery, they can be used to make a drug more absorbable or have a more targeted delivery, which are typically used by injections of the drug attached to these polymers. There are many more medical applications of biodegradables and many more to come. The slow breakdown of the polymer is also being used for delivery of agricultural chemicals as well. There are two types of biodegradable polymers, natural and synthetic. Listed here are a few of each natural and synthetic polymers. Some of the natural ones will be familiar to you. Although the natural polymers are grouped into two groups indicating where they are typically used, there is some overlap, such as different types of cellulose can be used for both medical and ecological uses, just different modifications of it. Same with starch. The synthetic polymers also have a variety of uses, such as PLA, as mentioned previously, is used for plastics, while synthetic PGA is used for medical applications. Although there are two types of polymers, synthetic polymers are the preferred choice. This is due to their mechanical properties, such as strength, and the ability to design them.
The reason why this topic is so interesting is because there are still so many discoveries to be made with research, and such amazing applications those discoveries can be used in. For example, Yin Yang owns his own transformative biomaterials and biotechnology lab here at Penn State. He focuses on materials used for regenerative engineering. Polyacetones, such as polycyclic acid, which is also known as PLA, are one of the few types of biodegradable polymers that have been widely used in FDA-approved medical devices. These medical devices include tissue engineering scaffolds or orthopedic fixation devices. Yang chose to innovate this material by making it intrinsically photoluminescent without adding traditional photobleaching organic dyes or cytotoxic quantum dots. Yang mentioned that this was a challenge, but he has resolved it. From successfully modifying PLA polymer to be intrinsically fluorescent, his lab has made a biodegradable material that can also be used in bioimaging, diagnosis, sensing, and other related applications. Another revelation made by the Yang lab was in making the PLA polymer mentioned previously into nanoparticles that can carry chemotherapeutic drugs to target cancerous tumors. Due to the fact that cell membranes of cancer cells overexpress folate receptors, the Yang lab explains that they can target those cells and tumors with their nanoparticle by conjugating folic acid on its surface. Also, now that the nanoparticle is fluorescent, which was also explained previously, the Yang lab can use the nanoparticle to image the tumors via fluorescence imaging. During surgery, a doctor can only see down to roughly millimeter-sized tumors, as Yang explains. Other cancerous cells near a tumor cannot be seen with the naked eye, and if those cells aren't removed, the cancer will return. Yin-Yang's nanoparticles can target the tumor cells, and then fluorescent imaging can be used to illuminate those cells for surgical removal. Yang also uses the fluorescent PLA polymer to create dual imaging nanoparticles that incorporate both cancer drugs and magnetic nanoparticles so they can be used both magnetic response imaging, more commonly known as MRI, and fluorescence imaging. MRI lets one look deep into the body and rapidly locate a solid tumor, and then fluorescence imaging enables doctors to identify small cancer cell clusters around the tumor areas.
Now that we've discussed applications, let's finish off with the advantages and disadvantages of biodegradable polymers.
As mentioned before, synthetic polymers are desired. Some advantages that synthetic polymers offer are tailorable properties, predictable lot-to-lot uniformity, free from concerns of immunogenicity, and reliable source of raw materials. Synthetic polymers offer engineers the opportunity to design them. An engineer has a responsibility of making sure that the material must not evoke a sustained inflammatory response, possess a degradation time coinciding with their function, have appropriate mechanical properties for their intended use, produce non-toxic degradation products that can be readily resorbed or excreted, or include appropriate permeability and processability for designed application. Making sure the material meets this criteria is a challenge because this criteria is largely affected by the material properties, such as material chemistry, molecular weight, hydrophobicity, surface charge, water absorption, degradation, and erosion mechanism. As mentioned previously, biodegradable polymers offer the significant advantage of being able to be broken down and removed after they serve their function. This opens up the window of the vast amount of chemical applications such as surgical sutures and implants. Another advantage is that biopolymers limit carbon dioxide emissions during creation and degrade to organic matter after disposal. This is a huge breakthrough for environmental sustainability. A disadvantage is that this field requires significant time and resources to complete research on this non-trivial topic. Given that all of the research and time are provided by resources, there is still one disadvantage, and that is cost. Environmental responsibility has become increasingly important to both consumers and industry in today's society. Although synthetic plastics are a more economically feasible choice than biodegradable ones, an increased availability of biodegradable plastics will allow many consumers to choose them on the basis of their environmental responsibility.
Another key disadvantage of biodegradable polymers is disposing of them. A study done by a university in England, Loughborough University, found that oxo-degradable plastic bags cannot be recycled with regular recycled bags. These researchers found that if oxo-degradable bags are mixed in too much with regular recycled products, these recycled products would be sustainable to degradation. This concept can also be applied to other types of biodegradable plastics. Certain biodegradable plastics are meant to be disposed of in compost to increase efficiency of degradation. If not disposed of in a compost, these biodegradable plastics can sit in landfills for long periods of time. It is a rarity to find these composts in large urban cities, which leads to many biodegradable bags sitting in landfills and decreasing their efficiency. Take, for example, polycaprolactone, or PCL for short, a starch blend biodegradable polymer. In an experiment done by the Science for Environment Policy, this PCL blend bag was left in aerobic conditions for periods of time. After 44 days, it was found that 88% of this PCL blend bag was degraded. This same PCL blend plastic bag was left in landfill or landfill conditions. After 90 days, the scientists began to see small pin-sized holes in the bag beginning to form. This concludes while the PCL blend bag does biodegrade in most conditions, it will take much longer, thus decreasing its efficiency under landfill conditions as opposed to aerobic. To conclude, we have discussed a vast amount of information today. We went over what a biodegradable polymer is and what it means to degrade. We then talked about the chemistry behind biodegradable polymers and the mechanisms involved. We dove into the applications and the numerous advantages of biodegradable polymers, and finished with some disadvantages and some drawbacks. While this is exciting research, there are still drawbacks that need to be fixed. The need to reduce plastic waste from landfills has ignited a fire towards research into biodegradable polymers. Countries all over the world are investing time and money into this research, and the progress has been exciting. Although the change from traditional plastics to biodegradable ones won't be quick, biodegradable polymers are sure to become used more and more as research and new technology progresses.